All right. Um, Today we start talking about mechanical design of the principles of mechanical designs. In the context of later, we're going to talk about kinematics and dynamics of machines. To talk about mechanical design, we start by talking about stress analysis. The the ultimate goal of a stress analysis is to design load carrying machine elements or design safe load carrying machine elements. There are some steps that we follow to design safe load carrying machine elements. The first step is to find the loads carried by each machine element. Once we've done that, we identify the critical point in each member. And once we identify the critical point, we evaluate the stresses at that point, and then we apply failure criteria, failure theories or failure criteria to determine the integrity of element, meaning that we plug in our stress component, stress values into this criteria, and we determine if the element is safe for the load it needs to carry. And we can also evaluate the safety factor. And we can design then for a certain safety factor. To determine the stress components, what we do in mechanics of deformable solids or strengths of materials is to define an infinitesimally small cube from the element around that critical point. And we orient this cube such that its faces are aligned with the coordinate system, meaning that each face of this cube is normal to a coordinate axis. And because each pair of these faces are normal to the same axis, we can essentially define 6 independent planes. A cube has 6 faces, and each pair of these planes are normal to the same coordinate axis. For example, 2 planes are normal to the x-axis, 2 planes are normal to the y-axis, and 2 planes are normal to the z-axis. So we have 6 independent planes, and for each plane we can define 3 stress components. 3 independent planes multiplied by 3 stress components. For each plane we can define 9 stress components. In its most general case, we have 9 stress components. For example, for plane X, or the plane which is normal to that coordinate axis X, we have 2 in-plane stress components, tau xy and tau xz, and one normal to the plane stress component sigma xx. The normal component is always along the corresponding coordinate axis, meaning that for the plane x, sigma xx is along x-axis. Tau xy xz represents the shear stress on plane x along z-axis, and tau xy represents the shear stress on plane x along y-axis. Now, question is, we have non-stress components. Is there any mathematical object we can use to describe this property stress? By definition, tensors are mathematical objects which include an array of components which are functions of coordinate space. So we use a 3x3 tensor to describe stress at the critical point. Again, we have already identified the critical point, although you can define a stress for any point in a mechanical element. And we arrange the stress in this stress tensor such that the diagonal component represent normal stresses and the off diagonal component represent shear stresses. Now note that you could use a different notation. For instance, you could use sigma 1 instead of sigma xx. You could use sigma 2 or sigma 3 instead of sigma zz. It's just a convention. And note that in this notation, the first subscript indicates the plane on which we are defining the stress for, and the second subscript defines the direction of the stress. So plane X, the stress along y-axis. Plane X, the stress along z-axis. Plane X, stress along x-axis. So if you just remember the convention, you're going to be able to say which one is normal stress and which one is shear stress. Because if you're on plane X and the stress is along X, then it means that this stress is normal to the plane. If we write a static equilibrium equation, meaning that if we use the force balance equation, sigma F equals to 0, and moment balance equation, sigma M, about the axis normal to a plane equal to 0, we deduce that shear stresses tau xy is equal to tau yx. Same thing about tau xz being equal to tau zx, and tau yz is being equal to tau zy. So if we go back to our 3x3 tensor, we realize that having these components equal to each other makes this tensor symmetric. So this stress tensor is symmetric. Now, if there are no forces in the z direction, meaning that sigma z equal to 0 and sigma x z equal to 0 and sigma y z equal to 0, and as a result of symmetric structure of the tensor, sigma zx is also equal to 0 and sigma zy is also equal to 0. It means that we now have a 2 by 2 stress tensor, or a two-dimensional stress tensor. So if our loading is such that there are no forces in the z direction, we are going to have a 2D stress tensor. Now, if we apply the load such that our load goes the centroid of cross-section of this element, the cross-section of this element is going to look like this. So if for this element, this force goes to centroid of cross-section, if this element has a uniform cross-section, the cross-section is fixed, it doesn't change. And if the material is homogeneous, then we are going to have this special case, which is a direct uniaxial stress. This is essentially the simplest case we could experience. If P is positive, then it means that we have a tensile stress, and if P is negative, we have a compressive stress. As a result of tensile stress, we could pull on the element. We could essentially change the volume of this element, but either by compressive or a tensile load. Also, the compressive load may result in the crush of the element. And the last thing is, for that simple case, we can deduce that the elongation is going to follow this equation. Elongation is going to be PL over EA. A is the cross-section area of the member, P is the force, L is the length, and E is elastic modulus. How we find this equation? If we have, for an elastic material, we can apply Hooke's law. Hooke's law is sigma equals E epsilon. Epsilon is a strain, and sigma is uniaxial stress. Sigma, by definition, is P over A, and epsilon is delta L over L. So now use these two relations and derive this relation for elongation. Thank you for watching this video, and see you next time.